This is the third part on the topic 10 multivariate linear regression, and the focus is obviously going to be on this lab notebook. So this is me explaining how you perform multivariate regression, and when I'm done with all of this Python notebook, then you can get started on lab 10. So, like always, we will import the packages we need. And you're familiar with many of these, but the new ones are this, which is Seaborn. So it's used for exploratory data analysis, which you will see shortly. And we are importing it as SNS. So anytime you see SNS, you know you're going to be using the Seaborn package. There is also the stats models package, and we're drilling down to the class we need inside the package, and we store all of that as SMF, which we will use for multivariate regression. It obviously can also do linear, sorry, bivariate linear regression. So the same package you use for multivariate linear regression can do linear, can do bivariate linear regression, because the only difference is with multivariate linear regression you have multiple variables, but with bivariate linear regression you only have two variables, x and y, and you will see those shortly. So we will import a CSV file which has data from the Gulf of Mexico. So this is actually real petroleum engineering data. It has numbers with a comma to signify thousands, and we don't want that to get into the numbers because it can screw the numbers and it wouldn't treat them like integers or floating point numbers. So we remove the commas using this second argument. So this second argument tells it when you see a comma, it's not a string, it's just signifying that the number is in thousands. So that's the importance of this second argument. And after importing it, we can print out the data frame by typing out the data frame as the last item in the cell. And when you run it, you see this, and this is what the data looks like. Several rows, several columns. Field name, these are the columns. New field, this year, discovery year, water depth, and all of that. Important thing is, like you're going to see in a real data set, there is always going to be issues. So there are columns with no values. NaN stands for not a number. So this is basically garbage. And that's not the only garbage here. We also have the entire last row filled with garbage. So we need to be able to handle these million data set. That's one of the important things we need to do before we even get to the point of performing linear regression. And this is very important in the fields of data analytics, data science, and all these new buzzwords you see all over the place. It's very important. These are the active fields recruiting very actively these days, so it's what you get the experience during this course. So row 50 is not useful. We remove it. How do you remove it? The drop function, which we talked about before, you specify what row you want to remove. So we are removing row 50. Again, remember, this data actually starts from row 0 because Python indexing starts from 0. So although it's row 50, it's the 51st row. And we can print it out and notice it's going to remove this entire row, and the last item will now be the 49th row. So the former row 50 is gone. Now this is row 49. So that's how you remove you remove rows that are not useful. To easily access the different columns, we can grab all the column headings by using the keys function. So the keys function just grabs the column names which we saw at the top of these data sets. So these, grab all of these and display them so we can start copying and pasting these to grab whatever part we want. So if we want field type, we use this. So we just copy this and we can search for when the field type is equal to gas. Because the field type is this column, you see it's either O or G. O for oil, G for gas. So if we want to grab only the data sets, meaning the rows where the field type is gas, we'll use this trick. Field type, grab that entire column and compare it to G. So when it is true, grab the data frame. So it's basically going to go in there and grab this, leave out this, leave out this, leave out this, leave out this, grab this, and it starts from the top down. And when you do that, this is what you get. Now you see all the field types are having gas. So that's how you grab the data set that have certain field values, basically. Now we want to drop some of the columns. So we are obviously going to drop this column, and some of the other columns that are not useful. And this is how we drop them. You specify the drop. Previously you dropped rows, right? We just specified the 50th row. To drop columns, you have to type in columns equal and provide the full name of all the columns you want to drop in a list. And that's rank new field, and we grab them from here, copied and pasted them here exactly as it is. So with all the spaces in between, that's fine. We just need to match, and Python will drop those, and you're going to be left with what is shown here when you use the df1 to grab or to display the content of the data frame. And this is what it looks like. Now you have clean looking data set, and now you're in a position to do your exploratory data analysis and your linear regression, which we will talk about shortly. Scatter plots are nice. You can easily get your scatter plot by doing plt, which is your matplotlib.pyplot function. Sorry, matplotlib.pyplot. That's the class. Matplotlib is the package. Pyplot is the class, and you save that into plt, and it has a scatter function in it which can plot any column or any, say, collection of data against another collection of data. So here we're plotting one column against another column. We're plotting water depth on the x-axis, field gas oil ratio on the y-axis, and it looks like there is no direct pattern. How do you draw your linear regression? This way or that way? So the correlation coefficient of this regression of df1 of water depth against field gas oil ratio will be low. We also remember how to use the describe function, which gives you these descriptive statistics. And now you can actually grab the correlation coefficients, which is the R value for all of the possible combinations. So this was just water depth against field gas oil ratio, but there are several other variables, right? You can get the correlation coefficient for these two for water depth and field gas oil ratio for water depth and proved oil. Basically all combinations of two different columns. And how do you do that in a systematic way? Use the correlation function, CORR. So you put a dot right after the data frame, and it knows to go into the data frame and compute the correlation coefficient for each pair of columns in the data set. And that's what is shown here. So water depth against water depth, right? Then start plotting water depth against all the other ones. So this is water depth against field gas oil ratio, against proved oil, and you exhaust all of the columns. Then you go to the second variable, which is field gas oil ratio, and you calculate the correlation with all the other pairs. And the interesting thing is, this is water depth against water depth. And what will the correlation coefficient be? 1, 100%. It is a perfect correlation, because when you cross plot the same data against the same data, yeah, it's identical. It's going to be 1. Same deal for this. It's field gas oil ratio against field gas oil ratio. So as you go along the diagonal, you're plotting the same variable against itself, so it will always be 1. But these other ones typically follow the discussion we had before, right? If this is close to 0, then it means there is no correlation between those two variables. If it's close to 1, like say this, almost 100% positive correlation. If it's also close to -1, it's a strong correlation, but it's a negative correlation. So one variable increases as the other decreases. And this is the entire correlation matrix. How about actually plotting it? So that was calculating the correlation coefficient, and it used the correlation function, which was basically data frame dot CORR. Here we're using pair plot from Seaborn. So from Seaborn we use pair plot and provide the data frame as an argument, which is different from the approach here, because this was basically in pandas data frame, right? Pandas data frame dot the correlation function. Here you're using Seaborn to give you all the scatter plots for each pair of data in all of the columns, and you use the plt.show as usual, and you get the scatter plot. So remember, this high value, it's the sixth column, 1, 2, 3, 4, 5, sixth column, third row. How does that look when you actually look at the scatter plot? Right here, third row, sixth column, very strongly linear, which is exactly what we had talked about before. Strongly linear, it's going to be close to 1. Why are these looking different? Because on the diagonals we're cross-plotting water depth against water depth, field gas oil ratio against field gas oil ratio, same value on the x and y. So rather than just showing a straight perfect line, we show the histogram of that variable, which is more useful, and that's what you get on the diagonal. So this is a scatter plot of everything with everything, and you get it by using the pair plot function from the Seaborn Python package. Okay, we move forward. Here we want to create a smaller subset, and we put that into a different data frame called df2. And to remind you all, this is how we create a data frame from what type? From a dictionary. So this is how you signify dictionaries. Dictionary comes in key value pairs. The key will be used. It's not responding as fast as I want for some reason. The key will be used as the column title. So that's the key we choose, which we end up displaying here. And what data do you want to go in that column? Well, grab the column titled remaining oil from DF1 and put that there. That's your first column. Second column, title it GOR and grab field GOR. All these weird looking text came from the input Excel sheet. Same thing for QMoil. So you exhaust all of the data you're interested in putting into the second data frame, and it's just 4 of them. So grab all 4, and it's sitting in DF2 now. You can type in DF2 below this on your computer and see the full list of the 4 columns. But obviously that's not what we're displaying here, right? What are we displaying here? The correlation coefficients. So like before, but now we reduce it to only 4 columns. So all possible pairs. Everything is as explained before, so no need to talk much on these. Just wanted to bring it down to a smaller data set which is more manageable. And those are your correlation coefficients, and these are the corresponding scatter plots. So it's called pair plots, but it basically scatter plots each variable with every other variable. And all of this is what is called exploratory data analysis, EDA. So you hear about the term EDA, exploratory data analysis. You all know what exploratory variables are, right? Those are your x's. The y is your response variable, which is also known as your dependent variable. The x, we said, was also are 2 names basically, independent variable or exploratory variable. So when we are looking at exploratory data analysis, we are basically analyzing the x's. And the fact is, in many cases, they're actually not independent. In many cases, they are interdependent. And how do you find out if they are interdependent? Precisely using this function. So for instance, that variable that had a very strong, this, it means the variable sitting in the 6th column is dependent on the variable in the 3rd column. So proved oil is dependent on cum oil and vice versa. So they're actually interdependent, and that's why we use the word exploratory variable, because sometimes your x's are actually interdependent. So we just say they are exploratory variables. And this is how you find out if they are interdependent. And this entire process, which is basically using the correlation function and the pair plot function, does allow you to do exploratory data analysis. So now we move on to do quick, simple linear regression by using this package, SMF. It's from Stats Models. OLS means ordinary least squares. So we're doing ordinary least squares regression, which we talked about in the slides. This is your your exploratory variable, your x. This is your response or dependent variable, your y. We choose it to be remaining oil. Here I want to find the regression between or fit a straight line through these 2 data. So this is bivariate linear regression. Start models.ols. Y comes in first. Important to pay attention to that. X comes in second, and this is Pythonic, so you use a dot after that and you call the fit function. So it fits a straight line through a plot of x against y, a plot of y against x. And that is stored in model, and we can use the model, which is your straight line model. You use the predict function on it and you provide your x. So now your y model, which we talked about before, it was y with the hat on top, right? That is this, your prediction. And y here is your data. So you can compare those 2. We can also check out a summary of how reliable this linear regression line we have drawn through the data set is. So how do you quantify that? One of the metrics is the R squared value. And R squared is precisely your correlation coefficient squared. Adjusted R squared is more relevant when you have more than two variables, so multivariate linear regression. This is archaic information criteria. This is Bayesian information criterion, which we are not going to talk about in this course. And the important one we've talked about before is your p-value. It needs to be less than what value for it to be significant? P-value needs to be less than 5% for your model to be statistically significant. So take note of that. We'll use it when we talk about multivariate linear regression. And I want to stop here so the video doesn't get too big.